Dear students, in this video on ray optics, we will study refraction at spherical surfaces, lens maker's formula and numerical problems based on them. So, let us begin with refraction at spherical surfaces. So, let us look at spherical surfaces first. See, a spherical surface is somewhat like a part of a sphere, like this is a spherical part, and this side the medium is continuous. This is your denser medium, and this is also a part of a sphere only, concave, and this is the denser medium. Like, say if I can complete a circle like this, then, and if this had been continuous like this, and from this cylindrical glass, if this sphere is removed, then this part becomes concave spherical surface. Similarly, if I could complete a sphere like this, then this part, this whole thing is convex spherical surface. So, you can see that a spherical refracting surface is a part of a sphere of refracting material. So, here we have shown this as denser medium, this is rarer medium. It can be air, and see, okay. Now, the center of the spherical surface is called pole, like this is also a pole, and center of the sphere is called its center of curvature, right? And the line joining the pole and center of curvature is called principal axis, like AB is principal axis. Similarly, here this is center of the spherical surface, which is called pole, and if I can complete this sphere, then its center is center of curvature, and the line joining these two becomes the principal axis, right? And from pole to center of curvature, we have radius of curvature. From this pole to center of curvature, we have radius of curvature. So, these are some of the definitions that we will follow. Radius of curvature. And now, while taking the refraction at spherical surfaces, we will take object as very small point object lying on the principal axis. The incident and refracted rays make small angles with the principal axis, and then the aperture or diameter of the curved surface is small. See, if this is like this diameter is very small. Here the object is very small, and these angles that it makes and all the angle of incidence and refraction, they all are very small. And new Cartesian sign conventions, you are familiar with them, then just for the sake of revision. First one, the incident ray is taken from left to right. This is direction of incident ray. Then all the distances are measured from the pole, and the distance measured along the direction of incident ray are taken as positive, and the distances taken against the incident ray are taken as negative, and the vertical distance above the principal axis is taken as positive, and the vertical distance below the principal axis is taken as negative. Now, here, just look at it. So, if I consider this, say, convex spherical surface, then you can see that the object is lying in air and the direction of incident ray is this, and here the radius, the center of curvature lies inside. So the radius of curvature is positive because it is measured along the direction of the incident ray, and the object distance is opposite to direction of incident ray, right? Similarly, if I take a concave refracting surface, then the center of curvature lies in the air and the pole is here and direction of incident ray is this, from left to right, then the radius of curvature is measured opposite to direction of incident ray. So the radius of curvature here is negative. And see. So let us start with refraction at a convex surface from denser to rarer medium. So we will look at the image formation first. The object is placed in rarer medium. You can see the pole, a center of curvature, and the object O is placed in air, and you can see that, see here, this is incident ray in air, this is refracted ray in denser medium. See how it is formed. Okay, so now if you see, the light ray is traveling from this object O at this point A. Now at this point A, the light has to enter denser medium. So first we will draw a normal at this point, and you know that the normal must pass through the center of curvature. If you have any sphere, then the normal to the sphere will be along the radius, right? And it will be perpendicular to the tangent. So the normal is always passing through the center of curvature for whatever location you may choose, right? So you draw the normal NC, and the original path of incident ray is this one, but you know that when light enters from rarer medium to denser medium, it bends towards the normal. So the original path of the ray is this, and normal is along this in denser medium. So the light bends towards the normal and it moves along this path, right? And so one ray is this, and if we take another ray which is moving along the principal axis, just look at it, it is moving along the normal because it is passing through the center of curvature. And you know that a light ray which is incident along the normal does not deviate from its path. If you remember this situation, if a light is incident along the normal, it does not deviate from its path. So the laws of refraction remain same everywhere, whatever be the shape or size of the refracting surface. So this ray OP will not deviate from its path because it is coming along the normal. And at this point, these rays, this one and this one, they meet, and you know that the image formed by actual meeting of rays is called real image. So a real image of this object O is formed in denser medium. So that is the working of this image formation. And see, the angle between incident ray and the normal is called angle of incidence. So this angle is angle of incidence, and the angle between refracted ray and normal is called angle of refraction. So this is normal and this is refracted ray. So this is angle of refraction. And we need to mark some more angles for the sake of derivation. So this incident ray makes angle alpha with the principal axis, and the refracted ray makes angle beta with the principal axis, and the normal makes angle gamma with the principal axis, and the distance between pole to center of curvature is radius of curvature r, and the object distance is taken from pole as u and image distance from pole as v, and the perpendicular distance of this point A from the principal axis is h. Okay, so I hope you understand this working of formation of image. So let us read it. Now, light ray from object O enters denser medium at point A. Right? Inside denser medium, ray bends towards the normal, as you can see. Now, ray coming along the principal axis does not deviate from its path because it is coming along the normal. And these rays meet at a point I to make a real image. So that is the working, and let us get into its derivation part now. So one by one, if you look at triangle OAC, this triangle OAC. Now you see that the angle I, this angle, if you extend this part here, then angle I is external angle and angle alpha and gamma are internal opposite angles. And you know that the exterior angle is sum of interior opposite angles. So I is equal to alpha plus gamma, property of triangles. Similarly, from triangle IAC, this triangle, look at it. Now here in this triangle, if I extend this line, then this gamma is exterior angle and R and beta are interior opposite angles. So exterior angle gamma is equal to sum of interior opposite angles R and beta, as you can see from here, right? And so we have considered two triangles here. Now from here we have got angle I, angle of incidence, and from here the angle of reflection R is gamma minus beta. And since refraction is taking place, so we have to apply the Snell's law. So applying Snell's law, see, applying Snell's law, sin I upon sin R is equal to refractive index of second medium with respect to first medium, and second medium here is N2, denser medium, first medium is N1, right? And angles are very, very small, so this sin I can be written as I, sin R can be written as R, and I upon R is equal to N2 upon N1. This happens for very, very small angles. So angles are very small. Now from here, do cross multiplication, you will get N1I is equal to N2R. Put the values of I and R from this equation and from this equation. You get N1 into I is alpha plus gamma is equal to N2 gamma minus beta. R is equal to gamma minus beta. And now open the brackets here. Open the brackets and collect the terms of gamma. So you have gamma here and gamma here also. So collect the gamma. So when you open up, you will get N1 alpha plus N1 gamma. Take N1 gamma to the right hand side and that will become negative. So the right hand side becomes N2 minus N1 gamma, and on the left side you are left with N1 alpha, and from right side when you open up you will get N2 gamma minus N2 beta. Now take this minus N2 beta to the left side, it will become positive. So when you open up, you get this relation. N1 alpha plus N2 beta is equal to N2 minus N1 gamma. If you have any problem, you can do that in 2 steps. And now we will write values of alpha and beta and gamma. And these angles, alpha, beta, gamma, they are also very small. So alpha can be written as 10 alpha and beta can be written as 10 beta and gamma can be written as 10 gamma. For small angles, we can do it. So now I have taken, see, from this relation only, I can write N1 10 alpha plus, this should be plus N2 10 beta is equal to N2 minus N1 10 gamma. This should be plus. Please make note of it. And from here, if you look at the diagram now here, look at it. 10 alpha is altitude or height h upon base BO rather, but this P and B are very close because see the angles are very small, so P and B are very close. So the distance from B can be taken as distance from P. So the base for finding out alpha, the base becomes PO because P and B, these 2 points are very close, right? So this 10 alpha becomes this H upon PO, 10 beta becomes this H upon BI, and BI key, in place of BI we will measure from P, so PI, and for 10 gamma it will be H upon PC, right? So we are going to put these values here in this equation now. So N1 H upon PO plus N2 H upon PI is equal to N2 minus N1 H upon PC, and P and B are very close, right? And H is cancelled on both the sides. H is cancelled on both the sides, and if you look at this diagram once again, you can see that the direction of incident ray is this, and U is measured from pole. All distances are measured from pole. So it is measured opposite to direction of incident ray. So PO is negative, and the PB is along the direction of the incident ray. So PB, which is equal to V, image distance, is positive. So PB is positive plus V, PO is minus U, and R is also measured along the direction of incident ray. So PC is plus R. So from here, if I move on to this place, remember that this is plus, this is positive. So PO is minus U, PI is plus V, and PC is plus R. Now put all these values in this equation and then we get here N1 and as it is, H cancelled on both the sides, PO is minus U, PI is plus V, and PC is plus R. So I get this relation N1 upon minus U plus N2 upon V is equal to N2 minus N1 upon R, and just rearranging it, the final relation is here. Final relation is here. What is it? N2 upon V minus N1 upon U is equal to N2 minus N1 upon R. So this is equation for refraction at this spherical surface. Very important relation and derivation also. So you must remember it. Now, you can derive the same relation for different image formations. You will get the same relation in every possible case. Like here, refraction at convex surface only, but we can make virtual image also. So let's see how it happens. Look at this diagram first. Yeah. Your object is here object O. Object O is here. Now from here, light ray is traveling, and at point A, it is entering the denser medium. So at point A, first you draw this normal. First you take this normal, right? And since the light is an original path of light is this one, so it in denser medium it bends towards the normal. This is the normal position, it is bending towards the normal, right? So when it is bending towards the normal, but it is not bent enough to move to this side. So at this place, we will produce this ray in backward direction here, and it meets the principal axis at this point, right? And the ray from this object, when it moves along this pole, it will move straight to the center of curvature. There will be no deviation here at this point because this light ray is coming along the normal only, right? Now, when you are observing this ray and this ray from this point, if your eye is placed here, you will feel that the light rays are coming from this point. Actually, लाइट रे यहाँ से नहीं आ रही है, लेकिन आपकी आँख को यहाँ पर, इफ़ योर आई इज़ हियर, आपको लगेगा कि ये वाली लाइट रे और ये वाली लाइट रे इस पॉइंट से आ रही हैं, ठीक है? सो एक इमेज बनेगी वहाँ पर जो कि वर्चुअल इमेज होगी. वहाँ पर सचमुच में कुछ नहीं है, लेकिन आपको ऐसा लगेगा क्योंकि हमारा ब्रेन जो है वो इस तरीके से इसको प्रोजेक्ट करेगा कि लाइट इधर से आ रही है और इधर से आ रही है, तो यहाँ कोई सोर्स ऑफ लाइट होना चाहिए. अ ब्रेन इज डिजाइन दैट वे दैट इफ लाइट रेज आर कमिंग लाइक दिस फ्रॉम वट एवर सोर्स, और यहाँ से अगर आप देख रहे हैं तो हमारा ब्रेन खुद ही इमेजिन कर लेगा कि पीछे यहाँ से कोई लाइट सोर्स रखा हुआ है और वहाँ से लाइट आ रही है. सो अ ब्रेन इज डिजाइन दैट वे. सो वी obtain a virtual image at this point, right? And here, now this is incident ray, this is incident ray, and this is normal. So angle between incident ray and normal is angle I. This is refracted ray and this is normal. So angle between refracted ray and normal is R, and the angle which this incident ray makes with the principal axis is alpha, and angle which the refracted ray जिसको हमने पीछे प्रोड्यूस किया है इसके और प्रिंसिपल एक्सिस के बीच का एंगल बीटा, और एंगल बिटवीन नॉर्मल एंड द प्रिंसिपल एक्सिस इज गामा, राइट? एंड हियर द ऑब्जेक्ट डिस्टेंस फ्रॉम पोल टू ऑब्जेक्ट इज u, image distance from pole to image is v, and radius of curvature from pole to center of curvature is r, right? And according to sign convention, see the direction of incident ray is this, left to right, and the object distance is measured opposite to it. So object distance u is negative. Image distance v is also measured opposite to incident ray, so v is also negative, and r is measured along the direction of incident ray. See, so r is positive. So taking the sign convention properly for uv and r and writing equations for I and r from these triangles and using Snell's law, when you solve it, you will arrive at this relation, and you will be surprised to see that. So relation in this case is also the same relation, n2 upon v minus n1 upon u is equal to n2 minus n1 upon r. And you know that n1 is the rarer medium refractive index of rarer medium, and N2 is refractive index of the denser medium. Now similarly, we can take refraction at concave surface. So if you look at concave surface, the process and method is same. The laws of refraction are used exactly in the same way. Now here, the object is in rarer medium O, and when light ray from object reach the denser medium, then at point A it is entering the denser medium. Now at this point you have to draw the normal. Now the center of this concave surface is in rarer medium only. So at this point when you draw the normal is along this direction. Okay? And the original path of the ray is this one, and you know that light ray bends towards the normal. So the light ray bends along this direction, and then this is the refracted ray. This becomes the refracted ray, and obviously this light is not moving towards the principal axis, so you will produce it backwards. So when you produce this light ray, refracted ray backwards, it will meet the normal, the principal axis somewhere here, right? So when you produce the refracted ray backwards, it meets the principal axis at this point. And the light ray which is moving from the object along the pole and through the center of curvature, it is moving along the normal and there is no deviation. Now when your eye is observing from this point, see, when you are observing from this point, आपकी आँख में ये वाली रे जा रही है और आपकी आँख में ये वाली रे जा रही है, ठीक है? और जब इनको पीछे पीछे प्रोड्यूस करेंगे तो ये वाली रे ऐसा लगेगा कि यहाँ से आ रही है. You will feel as if these rays, the refracted ray and this refracted ray, they are coming from this point. And क्योंकि वो सचमुच में वहाँ नहीं है तो एक वर्चुअल इमेज बन रही है. It is not a real image, but our brain assumes that there is some image formed here. So a virtual image is formed at this point, and using the same rules for angle of incidence, like this is incident ray and this is normal. So angle between incident ray and normal is I. As you can see, this is I. Angle between normal and refracted ray is R. You can see here R. Angle between, now taking all other angles, like see, this is incident ray and the principal axis alpha. This is refracted ray and the principal axis as beta. This is normal and the principal axis as gamma. And looking at the sign conventions now, see, the direction of incident ray is this one. So R is measured opposite to direction of incident ray. So radius of curvature R is negative. The object is also measured, object distance is also measured opposite to incident ray, negative. Image distance is also negative. So all these are negative, and writing Snell's law and doing all that, you will reach the same relation. N2 upon V minus N1 upon U is equal to N2 minus N1 upon R. So we arrive at a situation that whatever be the shape of the reflecting surface, whether it is convex or concave, or image may be real or virtual, but when refraction takes place from rarer medium to denser medium, you always get the same relation. You have to do these derivations also following the same method. And now we will take refraction at convex surface from denser to rarer medium. Now we are having, now the object will be in denser medium. So first let us have a look at the image formation. Look at it here. Now we are taking refraction from denser medium to rarer medium. So object is placed in denser medium, and when light travels from this object towards the rarer medium, then at this point it is entering the rarer medium. So at this point, first you will have to draw the normal. Now center of this convex surface is here, C. So this is center of curvature. So from center of curvature to point A, this Cn becomes the normal at this point. And you know that when light travels from denser medium to rarer medium, it bends away from the normal. So the initial path of the ray is this one, and here is the normal. So it bends away from it, and the light ray travels along this path, right? And the another light ray which is coming through the center of curvature and through the pole is coming along the normal. So it does not deviate at this path, at this point P, and travels straight. So at this point, this ray and this ray, both the refracted rays are meeting at this point, and then a real image is formed at this point. So here a real image is formed. And if you see, we will follow exactly the same method. This is the incident ray and this is the normal. Then angle between incident ray and normal is angle of incidence. Angle between refracted ray and normal is angle of refraction. The angle between incident ray and the principal axis is alpha. Angle between refracted ray and the principal axis is beta. Angle between normal and the principal axis is gamma. So taking all the same assumptions, we can derive relations here also, and you can see that here the radius of curvature PC is R, the direction of incident ray is this one, so here R is negative. The object distance is opposite to incident ray, is this also negative, but the image distance is along the direction of incident ray, so it is positive. So considering all these assumptions, Cartesian assumptions and Snell's law, we can find out relation for it. So let us look at its working now. Light ray from object O enters rarer medium at point A, where the ray bends away from the normal. Now rays coming along the principal axis does not deviate from its path. These rays meet at point A to make real image. So this is the working in brief, and let us move on to its derivation part. See. Okay. Now, from triangle OAC, triangle OA, and this is C. If you look at this triangle OAC, then you can see that this gamma is exterior angle and alpha and I are interior opposite angles. So exterior angle gamma is equal to I plus alpha, this equation. And if you consider this triangle IOC, triangle IAC, triangle IAC, this triangle, then you can see that if I produce it like this, then angle R is, see, this angle for triangle IAC, this angle R is exterior angle and gamma and beta are interior opposite angles. So exterior angle R is equal to sum of interior opposite angles gamma plus beta. And now we will use Snell's law. So Snell's law is sin I upon sin R. Sin I upon sin R. And you know that sin I upon sin R is refractive index of second medium upon the refractive index of the first medium. But here the second medium is rarer medium. So second medium is N1 and first medium is N2. You can see denser medium is N2. So that you have to remember. And since the angles of are small, so sine I can be written as simply I, and sine R can be written as R, and this is equal to n1 upon n2. And now doing cross multiplication here, see, cross multiplication, you will get n2I is equal to n1R. And putting the values of I and R from this equation, so you can see that I from here is gamma minus alpha. So in place of I put gamma minus alpha, and R from that equation is gamma plus beta. So now open the brackets and collect the terms of gamma and alpha. So from here, if you look at it, from the left side you will get minus n2 alpha, and on the right side you get plus n1 beta. Take it to the left side, it becomes minus n1 beta, and on right side you get plus n1 gamma, and from left side this n2 plus n2 gamma is there. When you take it to the right, it will become minus n2 gamma, and taking gamma common, you will get n1 minus n2 gamma. So if you have any problem, you can do it in 2 steps. And now, since these angles alpha, beta, gamma, they are very, very small, so I can write alpha as 10 alpha, beta as 10 beta, gamma as 10 gamma. And here, taking exactly the same thing, if this perpendicular distance is h from A to M, then you can see that 10 alpha will be equal to h upon OM. See, M and P are very, very close. So we can take this OM nearly equal to OP. Similarly, that is object distance, and CM can be taken as PC, and IM can be taken as PI, and taking with right sign conventions. So here, now you can write minus n2 h upon PO minus n1 h upon PI is equal to n1 minus n2 h upon PC. And putting the values with right sign convention, and you can see the sign convention here. PO is equal to minus U, PI is equal to plus V, and PC is equal to minus R. So putting all these values, when you put them, you'll get N2 upon U. See, because U was negative, so minus N2 upon minus U will give you N2 upon U. From here you get minus N1 upon V, because V was positive, and from here you get N1 minus N2 upon minus R, right? And we will just rearrange these terms. I can write this here. Okay, let's see. Now you can see, just rearranging the terms, I can write N1 upon V minus N2 upon U is equal to N1 minus N2 upon R. N1 minus N2 upon R. So if you compare it with the previous equation, the positions of N1 and N2 are changed, remaining all are same. So here, expression for refraction from rarer to denser medium is same whether it is real or virtual, convex or concave. See, whatever be the shape of the reflecting surface, you will get the same result. And expression for refraction from denser to rarer medium, when the object is in denser medium, you will get the same relation, and the relation is, you see, compare these two. You can see that position of N1 and N2 are changed. Remaining all terms are exactly same. But you have to take U, V, R with right sign convention while solving numerical problems. So you have to do all these derivations and ray diagrams also. Now comes lens maker's formula. Using these ideas only, we can find out lens maker's formula. So here we have a lens, and see, the medium of lens is N2, which is denser, and it is placed in rarer medium N1, and okay, just look at it. So the lens is denser medium N2, rarer medium here N1, and our object is placed in rarer medium. This is the first refracting surface. You can see the light first reaches this first refracting surface, and its center C1 is on the right side, and after this point it is reaching the second refracting surface, and its center will be on the left side C2, right? And now the center of the first refracting surface P1, the center of the second refracting surface P2, right? So I hope you understand this. And now just look at it. Okay, here at this point L, the light ray is entering from rarer medium to denser medium, and this is its original path. Now at this point you have to draw the normal, and the center of this first surface is C1. So from here till point L you draw this normal N1, right? And the original path of the ray is this one, and light in denser medium, light bends towards the normal. So the path followed by the light in the denser medium will be along this direction towards the normal. So you can see that light is traveling here. The original path is this one, but it is bending towards the normal following this path. Now, if the medium had been continuous like this, अगर ये पूरा का पूरा N2 ही होता, तो लाइट रे स्ट्रेट चली जाती यहाँ पर एट पॉइंट I1, और यहाँ वाली जो लाइट रे है जो कि P1 के अलॉन्ग आएगी, वो सीधी 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 इस पॉइंट पे चली जाती, यहाँ दोनों के दोनों मिल जाते और एक रियल इमेज बन जाती. If this medium had been continuous, the light would have traveled straight to this point, and the light coming along the principal axis should have been along this direction, and they would have met at this point, and a real image would have formed. लेकिन ऐसा नहीं हो रहा है. So what is happening now? At this point, now the light ray is entering a rarer medium. So at this point I have to draw a normal first. So for the second surface, the normal is this one, C2 N2, right? And now this is C2 N2, and the light will bend away from the normal. So normal यहाँ पर है, original path ये है, तो light को इससे away bend होना है, away from the normal. So when this happens, see, you can see that the light has bent away from normal, and it is reaching the principal axis at this point, and light ray coming along the principal axis is also reaching here. So a real image is formed at this point. Now for the first refraction at point L, the object is O and image is I1. For the second refraction at this point, the object is I1 and image is I. That you have to understand. And now writing all the symbols which we are using along with their sign conventions. So at this, for the first refracting surface, pole is P1 and center of curvature is C1. So this is R1, radius of curvature R1. For the second refracting surface, pole is P2. center of curvature is C2. So the radius of curvature is R2 and the object distance is U here. For the first refraction, the image distance is V1 because this is the image. For the second refraction, the final image is formed at I. So the final image is shown, distance of final image is shown with V, and we have taken the average distances. We assume that the lens is very, very thin. So we are talking about thin lenses only. So let us look at the working now. Here. From object O, the incident ray at point L suffers refraction from rarer to denser medium, and bends towards the normal, right? Now, if the medium had been continuous, a real image would have formed at point I1, but at point N, the ray enters rarer medium from denser medium and bends away from the normal to make a final real image at I. Final real image at I. So that is the working of this thin lens. And now what we are going to do is, we will write formula for refraction at spherical surface. In the first case, from rarer to denser medium, and in the second case, from denser to rarer medium, and then we will combine them together. So that's how we are going to derive relation, which is also called lensmaker's formula. So for refraction at point L, U is U, object distance, V is V1, image distance, and R is equal to R1. And then the equation becomes N2 upon V1 minus N1 upon U is equal to N2 minus N1 upon R1. This is refraction from rarer to denser medium. And now, for refraction at point N, image I1 acts as object and final image is formed at I. So, object distance is equal to V1, image distance V is equal to V, and radius of curvature is R2 for the second refraction, which is from denser to rarer medium. So now the formula has changed. Here N1 upon V minus N2 upon U, or in place of U I have placed V1, is equal to N1 minus N2 upon R2. Now what we do is, we add this equation and this equation. Now when you add, you can see that N2 upon V1 from here and N2 upon V1 from here, this is negative and this is positive, they cancel out. We will have N1 upon V minus N2 upon V on the left side, and on the right side, if I take N2 here you have N2 minus N1, here I have N1 minus N2. So if I take N2 minus N1 as common, I will have 1 upon R1 from this term and minus 1 upon R2 from this term. So let us write it. So see, adding these equations, we get N1 upon V minus N1 upon U is equal to N2 minus N1 into 1 upon R1 minus 1 upon R2. And from here, take N1 common and bring it to the right hand side. So you will get 1 upon V minus 1 upon U is equal to N2 minus N1 upon N1 into this whole term as it is. And when you divide it, you get N2 upon N1 minus N1 upon N1. So N1 upon N1 gives you 1, and N2 upon N1 is refractive index of second medium with respect to first medium. That is refractive index of the glass of the lens or medium of the lens with respect to the outside medium. And the bracket term in bracket remains as it is. Now, When the object is placed at infinity, the image is formed at the focus according to the definition of focus. So if you supposing if it is convex lens and if the object is at infinity, the image is formed at the focus. So you can see that when u is infinity, then v is equal to f. This image distance is equal to f. So using this idea, when I put this u is equal to infinity, 1 upon infinity gives you 0. V is equal to f, you will get 1 upon f, and then we obtain the lens maker's formula. And you see, the lens maker's formula becomes, from the left hand side we get 1 upon f, from right hand side I can write it as n2 upon n1 minus 1 into this, the term in bracket, 1 upon r1 minus 1 upon r2. This is the lens maker's formula, you can see. And this lens maker formula is available for all kind of image formations. It is applicable to convex lens as well as concave lens. Very, very important derivation. And let us do some numerical problems based on them only. So starting with a very simple numerical problem. The radii of curvatures of an equiconvex lens are 15 cm each. Find its focal length, and mu of glass is given to be 1.5. Now, let us assume that this is an equiconvex lens. Now, equiconvex lens, this is the first surface, its center of curvature is C1, and the distance from this is R1. This is the second surface, its center of curvature is here, so the radius of curvature is R2, and direction of incident ray is from left to right, this one. Okay, we should be very clear with the sign convention. So from here you can see that this R1 is along the direction of incident ray, so R1 is positive, and R2 is opposite to direction of incident ray, so this R2 is negative. That you must remember. That is why I have shown you this diagram. So for convex lens, R1 is plus 15 centimeter. Equiconvex means they both have same radius of curvature but on the other sides, and R2 is minus 15 centimeter. Very important point to note. And now using the lens maker's formula, 1 upon f is n2 upon n1 minus 1 into 1 upon r1 minus 1 upon r2. And if we assume that the lens is placed in air, so for air n1 is equal to 1. So when n1 is equal to 1, this becomes refractive index of glass straight away. So n2 is equal to 1.5. So now from here we get 1 upon f is equal to mu of glass minus 1 into 1 upon r1 minus 1 upon r2, and put the values. So from here you get 1 upon f is equal to 1.5 minus 1 into 1 upon r1 plus 15 minus 1 upon r2 minus 15. So these two minus and minus give you plus, and you get 1 upon f is equal to, see, 1.5 minus 1 is 0.5 into, when this becomes positive you get 1 plus 1 2 upon 15, and 2 into 0.5 is equal to 1 upon 15, and take the reciprocal, focal length is 15 centimeter. So here what is really important is to understand the signs of R1 and R2, and from here it is very clear that the focal length of a convex lens in air will always be positive. So in air the focal length of convex lens is positive. And now, what if the lens was a concave lens? Now, the radii of curvatures of an equiconcave lens are 15 centimeter each. Find its focal length in air and mu of glass is given to be 1.5. And look at this diagram now. Now here, this is the first reflecting surface and this is the incident ray. So for the first reflecting surface, the center is C1 is on the left side and radius of curvature is R1, which is opposite to incident ray. So R1 is negative. For the second reflecting surface, the center is on right hand side C2 and the radius of curvature is along the direction of incident ray. So R2 is positive. So here the signs of R1 and R2 are changed. So now look at it. For concave lens, R1 is minus 15 centimeter, this one. R2 is plus 15 centimeter, this one. And putting the values, you get 1 upon F using the same lens maker formula. And putting all the values, you get 1 upon F is equal to 1 upon 1.5 minus 1 into 1 upon minus 15 minus 1 upon 15. And from here, look at it. 1 upon F becomes, this is 1.5 minus 1 as 0.5. And see, this is minus 1 upon 15 minus 1 upon 15 give you minus 2 upon 15. That is minus 1 upon 15. Taking reciprocal, F is equal to minus 15 centimeter. So in air, the focal length of concave lens will always be negative. And very interesting problem here. The radii of curvatures of an equiconvex lens are 30 centimeter each. Find its focal length. The refractive index of glass is given to be 1.5. Find its refractive index when this lens is dipped in a refractive index of medium 4 upon 3, which is water. आपके convex lens को water में dip कर दिया. Second case, it is dipped in a medium of refractive index 1.5. And third, it is dipped in a medium of refractive index 2. So let's see what we get. अब हम बाहर वाला medium change कर रहे हैं. So for convex lens, equiconvex lens है, air में हम लेंगे तो R1 हमको पता है plus 30, R2 is minus 30, and using lens maker's formula, you get N2 upon N1 minus 1 and into this thing, and here N2 is given to be 1.5. See here. So and N1, the medium here is 4 upon 3. So when N1 is 4 upon 3, outside medium is 4 upon 3, that is the lens is dipped in water. This is water and lens is dipped in water. So what you get? 1 upon F is, N2 is 1.5 and N1 is 4 upon 3 minus 1, and putting the value of R1 and R2, you get 1 upon 8 from here into 2 upon 30, and it is 1 upon 20, and taking reciprocal, the focal length becomes 120 centimeter. So the focal length in air was 30 centimeter, but in water it becomes 120 centimeter. But it is behaving like a convex lens only because the focal length is positive. And so focal length increases. Now, what if the outside medium is of refractive index 1.5? So now using the same relation, putting N2 upon N1 as 1.5 upon 1.5 minus 1, and bracket में सारा as it is है, this becomes 1 minus 1 0. So this whole term becomes 0, and taking reciprocal, focal length becomes infinite. So the lens behaves like a plain glass sheet. So you have dipped this glass lens in an outside medium which has same refractive index, then this lens behaves like a plain glass sheet, or we can say that the lens will disappear. It will not be seen at all. आपको लेंस दिखाई नहीं देगा, वो डिसअपियर होता हुआ लगेगा. And the third case, what if the outside medium is denser? N1 is denser. So you get 1 upon f is 1.5 upon 2 minus 1, and bracket wali term as it is here. So you simplify it, you get minus 1 upon 4 into 2 upon 30. Simplify, you get minus 1 upon 60, and f is minus 60. Now the focal length has become negative. That means the nature of lens has changed. So that means if the outside medium is denser, the nature of lens changes, and the convex lens will behave like a diverging lens. You know that a convex lens is like a converging lens. Light coming to it converges at one point. But here, if it is placed in a denser medium, then the light coming to it will diverge, move away from each other. It will behave like a concave lens. So nature of the lens changes. With this, I come to the end of this video, and I hope that this video is beneficial to all of you. Thank you very much for watching it.